Hello and welcome back. We're in Unit 4 on polynomials. This is the section 4.4 on special case factoring. This is the difference of squares special case factoring, which we're using Pizzazz page 84 as a practice page. And we're going to use the vocabulary words that we've been using in the past. So in this unit we have defined factoring as the process of breaking a polynomial into its component parts. So again, that definition of factoring is the process of breaking a polynomial expression into its component parts. And essentially, factoring is the opposite operation to simplifying. So make sure that that's on your page, that we have written in green here is the opposite operation to simplifying. The next vocab word we're using is difference of squares, which is the title of this section. So when we talk about difference of squares, we are talking about a special type of polynomial in which two terms of perfect squares are being subtracted. So again, a difference of squares is a special polynomial with two terms of perfect squares being subtracted. So for example, I'll give you a few examples here. Our first example is a squared minus 25. The second example is 16x to the fourth minus 49y squared. And the third and final example is 100w squared minus 1. Now, the important piece to recall in each of these is that the first term, along with the second term, is a perfect square, and then also recognizing that they are being subtracted. So in each of these situations, we have a subtraction between both the first term, which can be broken down into a perfect square, and the second term, which also can be broken down into perfect squares. And when we talk about perfect squares, I'll give you examples here momentarily after we talk about this method, but perfect squares are essentially integers in which we can find. So we'll talk about that in a moment. We'll discuss that, because it can also be variables and different types of variables. It doesn't just have to be a squared. As you have noticed here, we have an x to the fourth. So we'll talk about how you can break that down into becoming a perfect square. So without further ado, let's take a look at the method. And so we're going to look at the method for factoring difference of squares. And the first step in this method is to look to simplify. And essentially that concept is to factor the greatest common factor out, if this is possible. It might be possible and it might not be possible. So just look to simplify. The second step is to identify the factors of each perfect square. So we want to break the perfect square into its factors. And in order for it to be a perfect square, we're going to need to recognize that it needs to be the same thing. So for example, I might even just jump ahead for us and take a look. If I have an example where I have 1 times 1, this is a perfect square of 1 squared. Now 2 times 2 is an example of a perfect square 2 squared, which is the same thing as 4. Here this is the same thing as 1. These are just examples to remind you of what this looks like. So in terms of these integers that we have, these could be the coefficients along with many, many others as we keep going down here and continuing this indication. So lots of things to be thinking about, but those are, here we've got, these would be the perfect squares. And then over here, these would be the factors of those perfect squares. So just trying to indicate those pieces. So we're going to go back to this step-by-step method. All right, and the next step in this step-by-step method is number 3. We're going to place the factors of the first term into the position of each binomial and repeat the process for the second term. So the first term should be placed into the first position for each binomial. And we're going to repeat that process for the second term, and it will be the second term in each binomial. So again, we're placing those factors into that. The fourth step is to place addition and then a subtraction sign within the binomial. So we'll have a visual here for you. So the first binomial, we often place an addition sign, and the second binomial, we often place a subtraction sign. Now when we take a look at this, we leave this alone. It could be in which this binomial can be shifted over here, and this binomial can be shifted over here. They can be flip-flopped. The subtraction sign can be first, the addition sign can be first. The only thing that really is required is that we have one addition and one subtraction. For step 5, if we found a greatest common factor, we're going to place it in front of these binomials. So again, if we found a GCF in step 1, it's only if we found one. Then we're going to place it in the front of the two binomials. And finally, we're always going to look to see if we can further factor. So is there another GCF or a difference of squares? Yeah, is there another GCF or a difference of squares? So when we take a look at this, what we have kind of left out of here, which hopefully by now is second nature for you, is to check this by factoring, or this factor rather, by foiling. So hopefully we've gotten to that point where a check is a natural process. If it's not, you can absolutely add it in here as step number 7, right? So step number 7, you can always add in here as a check. And I can just plug that in here and say check with FOIL as a reminder for us. Now taking a look at that, the last thing on this page we want to do is I just want to list out some perfect squares, which I gave you a few examples of, but I want to recognize the difference between the factor and the perfect square, perhaps the coefficient that we might be working with. So 1 times 1 is 1 squared, 2 times 2 is 2 squared, which equals 4, 3 times 3 is 3 squared, which equals 9, etc. So as we go through here, we have these factors on this section, and let's see if I can make that actually fit. So those are the factors that are breaking up this perfect square over on this side. So these are the perfect squares again, and these are the factors of the perfect squares. So those are the factors for the perfect squares that are shown on the right. Now let's do a few more since these are important things just to have on hand. So this is a notes sheet, so it makes more sense to just throw them down. So we're going to go the rest of 9 times 9 all the way through 15 times 15. So please be sure to add these onto your page. And multiplication tables are definitely something that we want to keep in the forefront of our brains when we are doing this. So be sure to be working on your multiplication tables, as that will really help your factoring skills as we go through. As you have figured out factoring is that whole process of breaking down the polynomial expression, and it could be that our multiplication skills kind of hinder that process. So again, the factors in this set is this lovely row and the perfect squares. I didn't quite get everything in there. So the perfect squares, let's see. Oh, it's tight. Perhaps I can try it this direction. There we go. So there we go on those perfect square pieces. Okay, lovely. So looking at that, we are going to do a couple of examples together and then some try on your owns. So please flip the page and title it 4.4. And difference of squares, again, we're working in our factor unit. You know, another piece to just be sure that we are really solid on our vocab is difference means subtraction. So when we talk about the word difference, we're talking about the subtraction of two perfect squares. And under key concepts, I want to just throw out some factors of perfect squares that have some variables with them. So x times x gives us that x squared. X to the fourth and x to the sixth are also perfect squares. So here, these are those perfect squares. And then on this section right here, these are our factors of those perfect squares. So just something to keep in mind as we go along. Let's add a couple more to this realm. Again, I can break them up into, it's the multiplying itself by itself. So x times x squared times x squared, x to the third times x to the third. Reminding ourselves that these x's could be any variable at all, so we don't have to have them be x's. But kind of indicating the different ways again. Here, these are the factors of these perfect squares. So reminding ourselves the difference between the factor and the perfect square itself. And perhaps you've even noticed that, like in this case here, x to the fourth is a factor, a perfect square factor of x to the eighth, and it is also its own perfect square. So that is possible. Similarly, it's also, the reverse is also possible. So in this case here, x to the third is not a perfect square itself, but it can be a factor of the perfect square x to the sixth. So just something to keep and kind of wrap your brain around. And let's do a couple that maybe have some mixed variables. So let's take a look at x and y together. And we get xy times xy, giving ourselves x squared and y squared. We can also do some a's and b's, so perhaps let's do ab squared times ab squared. And that's going to give us a to the power of 2 and b to the power of 4. So if I take a look at that, that does make sense. And when I look here on this perfect square, I can recognize that I have an even number in each of my coefficients, in each of my exponents. And so that's a huge piece of how I can know whether or not a term, and again, this would be the term we would perhaps see in a polynomial, that we can recognize, hey, that's a perfect square. We can break that up into its factors of the perfect square. So that's important to kind of check in. And let's do one more where we have x and y again mixed together. This case we'll have x squared and y multiplied by x squared and y. Now this is going to give me x to the fourth power and y to the second power. So again, these are even exponents, so a 4 and a 2, letting me know that I can in fact break them up evenly amongst themselves. So that's kind of nice to work with. And let's go ahead and take a look at our first example. So example number 1 is x squared minus 9. And here we are going to work to break apart. I look and I say, hey, I don't have a GCF. There's no GCF. So step 2 was to identify the factors of each perfect square. And x squared gives me the factors of x times x. And 9 gives me the factor of 3 times 3. Now I do look and I have a difference, so they are being subtracted, and that's a huge piece to pay attention to. And since they are being subtracted, I can recognize that I'm going to place these into the binomials. So x is going to go into each first position, and the 3 is going to go into the second position of each binomial. Now I am going to place an addition sign and a subtraction sign involved in this. So one binomial has a plus sign and the other a subtraction sign. Taking a look at that, it helps me to recognize that I am working with a -9, as you see I've circled it in yellow. And -9, the other way you can recognize that, has the factors of -3 times a +3. So that's another way to recognize that, is not just working with the 9, but thinking of it as, well, this really is a -9 if I pay attention to the sign in front. So that's kind of indicating that. The next thing that we want to do is take a look. Okay, I didn't find a GCF, so I don't have to place anything in front. And I have no further factoring that I can do. There's not another difference of squares. Again, I would be looking at that here in this other subtraction. That's not a difference of squares, so good on us. And we can go to the second example. Before we move on to the second example, we do want to check in on the FOIL method. So we would check this using that FOIL, and in doing so I would recognize this whole process here of x times x in fact would give me that x squared term. X times -3 and 3 times x will give me 0 because they are opposites when I add them. And 3 times -3 in fact will give me -9. So that is kind of that intuition and that final check piece that we're working with. So let's take now a look at example number 2. So in example number 2 we have 7a squared minus 63. And I'm going to take a look and recognize, do I have a GCF? And in this case I do. It's a 7. And so when I take a 7 out, I am left with the terms a squared minus 9. And the a squared minus 9 looks very, very similar, if you recognized, to example number 1. And so that's a huge piece that we're working with, is just being able to recognize, hey, we've kind of done that before. So in this situation, the only difference is we have a greatest common factor. So I'm going to break this up, and my variable is a. So a times a and 3 times 3, just like I did in the example 1. And I'm going to place them into their binomials. And so the a's are in the first position and the 3's are in the second position. One is a positive and one is a negative, so I make them a plus and a minus. And I make sure that I drop down the 7. Now, because I checked example 1, we don't have to check example number 2. And I have this concept of 7 times the binomial x plus 3 times the other binomial of x minus 3 as my answer. On example number 3, we're going to do something slightly different. So we have 12a to the 6th minus 75b to the 4th. And I'm going to take a look, and I have a GCF here of 3. So I pull that GCF right out in front, and I place the remaining factors inside the parentheses. That recognizes that I have 4a to the 6th power minus 25b to the 4th power inside those parentheses. Now I'm going to say, well, hey, I'm working on difference of squares. Each term, I'm looking to see, is that a perfect square? And in fact, it is. I also want to look here and say, hey, is that a perfect square? Yes, it is as well. And is there a subtraction sign? So is there a difference? Yes. So doing that, I know I can break these up. And I find that 4a, whoops, let's pause that. 4a to the 6th power can be broken up into 2a to the 3rd times 2a to the 3rd. So again, 4, the coefficient there, is a perfect square, along with a to the 6th power is a perfect square. So I want to break those up evenly amongst the two terms, and that's how I know it is a perfect square, because it's the same thing multiplied by the same thing. That's what makes it perfect. And then similarly, the 25 can be broken down into 5 times 5, and b to the 4th can be broken down into b squared and b squared. So the next piece here is to place them into their binomial forms. So the first term is the 2a to the 3rd. So let's finish that off. And the second term is going to be b squared. Excuse me, 5b squared. Needs to go in both positions. One needs to be plus, one needs to be minus. And then that greatest common factor of 3, do not forget this, please. The greatest common factor of 3 is the piece that needs to go right out in front. So when I take a look at this, I can go through that whole foiling process, so that's what we're going to do next, to make sure that we get to a stage. And one of the pieces to recognize that we're working with here is this concept of I need to foil, and then I also need to take care of the 3 out in front. So the first goal when I foil is to make sure that I have this piece, and then I'm going to multiply by the 3 and hope that I finish off with my original polynomial of 12a to the 6th minus 75b to the 4th power. So when I do this whole FOIL process, here we go. I have 2a to the 3rd times 2a to the 3rd, and in fact get 4a to the 6th. 2a to the 3rd minus 5 times minus 5b to the 2nd. So that gives me a negative 10 a to the 3rd, b to the 2nd. And I recognize that 5b squared times 2a to the 3rd is going to be its opposite. So if I add opposites, they just go away, which is excellent news for me because I don't have a middle term in here. But I do want to check that I take 5b squared times negative 5b squared and get 25b to the 4th, which is in fact a true statement. Now if I distribute then the 3 through, I would check to see, hey, does this give me back the 12a to the 6th? And in fact it does. And over here, does this give me back the negative 75b to the 4th? And yes, again, in fact it does. So lots of checking that's going on throughout this process. So make sure that you are checking your work. Now example 4 is going to be slightly different. Again, working on building the differences amongst these types of problems, recognizing when this is a perfect square, when it's not, how to check that out. Example number 4 tells us 10x squared minus 121. Now I'm going to take a look and ask myself, is this a perfect square? And I'm going to say, hey, I think it might be because, well, 10 can be broken down into 5 plus 5, and those are the same, so maybe I can look at that. But then I remind myself, no, wait, factors have to be multiplied. So that would be 5x times 2x. And that would tell me I don't have a GCF, first of all. And when I break this up, 5x times 2x is not a perfect square. And because it doesn't have a GCF, it's also not factorable because it doesn't have a GCF and it's not part of this special case of difference of squares when I only have 2 terms. So in this case, I actually go to a not factorable situation. So we would consider this guy prime. So please also write prime here. All right. Let's take a look at a couple more examples. We have 3 more guided examples and 1 try on your own. So when we title this, we've got 4.4 difference of squares. And example 5 is going to be 200x y to the y squared minus 32x. Let's make sure we get the x in there. And our greatest common factor is going to be 8x. So when I pull the 8x out, that remains 25y squared minus 4. And so I'm going to break each of these up into finding those perfect squares. Again, if there is not a perfect square, that's fine. It's just factored as much as it can be because we found a greatest common factor. But in this case, 25 is like 5 times 5, and y squared can be y times y. So we're going to break this up into 5y times 5y, and 4 is the same thing as 2 times 2. So I'm going to place these into their binomials. So the first position is going to be the 5y, and the second position the 2. I'm going to have a plus sign and a minus sign. I'm going to make sure I drop down that 8x as my greatest common factor. In order for this to be completed, I need to have that 8x. It has to be there. So again, I'm going to check my work before I box in my answer. So multiplying 5y times 5y, I'm going to get 25y squared. And 5y times negative 2y is the opposite of 2 times 5y. Those guys go away, which is exactly what we want. 2 times negative 2 is going to give me that negative 4. Now if I go through this process again of distributing the greatest common factor, again we're trying to get back to our original polynomial. So if I distribute that greatest common factor one more time, I'm going to say, hey, 8x times, oops, I want a pen instead of a circle. Let's try that again. 8x times 25y squared, and I do in fact get 200xy squared. Yes, that's what we want. And 8x times negative 4, in fact, is going to come back to that original next term of negative 32x. Excellent ideas. We've gotten our check. It's taken care of. Let's go ahead and box in our answer of 8x times the binomial 5y plus 2 times the binomial 5y minus 2. Again, they look very similar. The only difference in the binomials is that one has a plus sign and one has a subtraction sign. Example 6 is coming our way next. So it's 2x squared minus 10. We do have a greatest common factor of 2, which then the remaining terms are x squared minus 5. We break up the x squared into x times x, and the 5, oh, bummer. The 5 is not a perfect square. The only options for the factors of 5 are 5 times 1. But it is factorable because it has a greatest common factor. So my answer is 2 times the quantity or the binomial x squared minus 5. So that's really important to recognize. This is not actually prime. It's just not able to use factor using difference of squares. Example number 7 is x squared minus 20y squared. This is not a perfect square in the second term. So 20 is not a perfect square, and there's no GCF in this between the two terms of x squared and 20y squared. So in this case, it's not a perfect square. There is no GCF. So again, not a perfect square, and there's no GCF. Therefore, it is not factorable. So if it's not factorable, again, we're going to write prime. So I'm going to go through there and write prime. Whoops, again, I don't want those circles. I do want a pen. Okay, so x squared minus 20y squared is a prime polynomial and cannot be factored. Here's the try on your own. It says 36x squared minus 100. So go through those steps, look for a GCF, try and identify if each term is a perfect square, what those factors are, and then place them into the binomials. Go ahead and check using FOIL, and I'll see you in class next time. We'll review. Thank you for your attention. Come prepared with full set of notes.